Limit points of a set. Let X be a metric space with metric D. If A is a subset of X, a point small x in X is called a limit point of A if each open sphere centered at small x contains at least one point of capital A different from X. For example, the set 1, 1 by 2, 1 by 3, etc. of R has 0 as its limit point. For the semi-open interval closed at 0, open at 1, X is a limit point of this interval for every X in between 0 and 1, including both 0 and 1, but the limit point 1 does not belong to this set. As another example, we can observe that Z, the set of all integers, has no limit points in R, and we know that every real number is a limit point of the set of rationals. Now, a subset F of the metric space X is called a closed set if it contains each of its limit points. First, we observe that both the empty set phi and the full space X are closed. We know that the empty set has no limit points, so it contains all its limit points and is therefore closed. Since the full space X contains all its points, it automatically contains its own limit points and thus is closed. The next theorem states that a subset F is closed if and only if its complement is open. For the proof, let us assume first that F is closed. Then we need to show that F bar is open. As a first case, let us assume that F dash is empty. We already know that the empty set is open. Now let us assume that F dash is non-empty. Let X be an arbitrary point of F dash. Since F is closed and X does not belong to F, X is not a limit point of F. As we know that a closed set contains all its limit points, X will not be a limit point of F. Since X is not a limit point, there will exist an open sphere, say SR of X, which is disjoint from F. That is, SR of X intersection with F is empty, so that SR of X is contained in the complement of F, that is F dash. Thus we have proved that for any X element of F dash, there exists an open sphere SR of X contained in F dash. Hence we can conclude that F dash is open. Thus we have proved that whenever F is closed, its complement F dash is open. Conversely, assume that F dash is open and we need to show that F is closed. For this, it is enough to show that every limit point of F is in F itself. So let us consider, say, Y a limit point of F. If Y does not belong to F, then Y definitely belongs to its complement F dash. Since F dash is open, we know that there will exist some open sphere centered at Y contained in F dash. Since Y is a limit point of F and the open sphere is contained in F dash, SR of Y intersection with F will be empty. Since every point of this open sphere is in the complement of F, the intersection of this open sphere with F will be definitely equal to phi. Thus we have obtained that SR of Y intersection with F is empty, but we have assumed that Y is a limit point of F, so every open sphere centered at Y must contain at least one point of F other than Y. But here we have obtained that the intersection is empty. So this must be a contradiction. Hence, Y must belong to F. So every limit point of F belongs to f itself, and we can conclude that f is closed.